Okay, we're gonna continue, our lecture to clip clip number 5, as appear on your screen. It's the first clip that we talk about partial differential equation. Okay, the previous 4 clip, we did talk about what we call the ordinary differential equation. And as you might know, that the differential equation is the equation that control that contain the derivative terms, and mostly the derivative term is dealing with only one domain, but as you might study from basic calculus that there exists some differentiation that contain multiple domain, and we call that the partial derivative. So partial differential equation is just the equation that contains the term that dealing with partial derivative, which means that you can have more than one domain, and then the resulting function that you are looking for or you want to find that satisfy the equation, might be the function that rely on multiple domain. That's what the definition of partial differential equation. So it's all type of equation that contain partial derivative term. And I just write a very basic, and I think that we can find many application in physics and engineering that we call the second order partial differential equation. We will abbreviate it form of the name as PDE. This one is like we have a constant a, time the second partial derivative of u function relies with respect to x, the second order, and also plus 2 times b, also another constant. Second order of u function. Certainly u will depend on both domain x and y. This one second partial derivative corresponding to x and y, the change of x and the change of y. And the third term is plus c, another constant, and second order, partial derivative with respect to y. And then minus, this one is another function that we call the capital F function, rely on domain both x, y, and also the u function themselves, and the first order derivative of u with respect to x and to y. So this is you can write in a general form, and we would call this as a linear partial differential equation if this function of f, capital F, is in this form. It's in the linear form that you can have a, this one, and the first 3 term is the same, but this function become like a constant, d times first order of u with respect to x plus another capital E constant, so first order of derivative of u with respect to y plus constant f times u function themselves, and plus a constant g is equal to 0. So this is the general type of what we call the second order linear partial differential equation. But you can have a third order, fourth order that most likely will become when you analyze second order statistically dealing with the variant function. It can be extended to the fourth order system. And so there can be a higher order system, but in this class, we will stick to this basic second order, and we will study a classical physics application that are related to engineering application. So we're gonna start with, this is the very basic and fundamental and classical PDE we call the one-dimensional heat equation. And this is a type of equation. We have a u function that depend on domain x and domain t. And the rate of change of u with corresponding to time t is equal to a constant value, positive value, alpha square, times the second order of u with respect to x. Okay, so there's two domain, x and t, and only one response of u. Okay, and with this we're gonna have some of the what we call the boundary condition. You remember that we need this condition, either initial or boundary condition, to make sure that you can finish and can write the function, okay, that satisfy this condition, okay, that can help you to find some constant in for the general form of the function. Okay, in this case, okay, we look at the time zero here. Okay, and x, domain x is between 0 and L. Okay, and you have ux at time 0 is equal to, certainly when you set up a domain t, some constant value, so this u of x0 have to become just a basic single domain function f of x. Okay, and u at x is 0 for any time t. Okay, this one is equal to u also at the boundary of x, okay, on both sides, the lower limit and the upper limit, okay, for any time t is equal to 0, or maybe equal to some constant or even some function of t. Okay, and that, okay, sorry, okay, we're gonna hold on, wait for a while. Okay, this one. Okay, but this one is the way we look at this problem mathematically. Okay, but actually this is a classic problem derived by physicians, mathematical physicians. Okay, we the problem what we call the one-dimensional heat equation. Okay, so suppose that in the physical side, u of xt is this function is the heat amount measured by temperature, for example, located at coordinate x at time t. Okay, if you look at this graph, okay, you can see how this function behave. Okay, when you have a domain x, okay, moving from in this direction from 0, okay, to the L value. Okay, so at u0 t, okay, at u0 for all t, t is a y-axis here. Okay, so this is the initial condition. You have initial condition here at the lower limit of x, and also you have the boundary condition here when x is equal to L. You have UL and T. Okay, for example, okay, you can measure in this. Suppose U is a temperature function. Okay, you know the temperature along the boundary, or maybe the surface of a product or surface of an object. Okay, here. Okay, at x is equal to 0, and also another surface as x equal to L for all time for all the time. Okay, it's a it can be a function that rely on the time t. Okay, or it can be a constant here. Okay, and you also know that, okay, along x axis here, okay, at time 0, okay, you have function of x here. Okay, that maybe in this case you might, oh damn, okay, you might look at this f of x is the initial temperature at time 0. Okay, in all coordinate of x. Okay, we start looking at this problem in a simple way by instead of looking the whole object as a 3 dimension, we just look at only one dimension. Okay, so to simplify the problem. Okay, therefore, okay, if u of xt is the heat amount, okay, located at coordinate x, okay, and domain x, okay, which is a location or whatever the dimension of the object at time t. Okay, therefore curl u, okay, curl by curl, as you know, the definition of derivative is the rate of change. Okay, so this is the rate of change of u, okay, over t, over time t, okay, for any specific point location of x. Okay, so this is a heat flow rate through time, okay, because it change over time. And also curve U by curve X, okay. This one is a heat flow rate through dimension of the object, okay, with the rate of change of the dimension of the object, which in this case we only consider one dimension of X. So this is curve U by curve X and curve U by curve T. So okay, so this is the starting for definition of heat equation, system equation. Okay. Okay. Next, you want to solve for U of X of T. Okay. Okay. So before that, we might take a look at that. So why this is become the equation. Okay. In this one, we're not gonna go through the derivation this directly, but you might take a look at this one. The relationship this hold that based on it become the governing law of the rate of change of heat, okay, over time and over dimension is that, okay, the change of heat, okay, over time, okay, is equal to, okay, alpha square is kind of, the dimension transformation from rate of change over time to rate of change over dimension. But rate of change over dimension is here. It's not in the first order, but it's the second order. Okay. So within the second order, it becomes acceleration. Okay. But it's acceleration over the dimension. Okay. Okay. And so alpha square is the way that transform the unit. Okay, the change of second order, the acceleration rate of, okay, rate of u, okay, over the dimension, okay, time a conversion unit alpha square, you get the rate of change of u over time. Okay, let's just say this is simple way, but if you want to know the reason of this transformation, you might go to Wikipedia, okay, and take a look at, just write down the heat derivation of heat equation. You will know in the physics course, okay, they will teach you that how mathematical physician can derive this equation. Okay, so you might look at this as u of x at time t, okay, rate of change of u over time is equal to, okay, some conversion unit time acceleration of u over the period, no, over the dimension that you are interested. Okay, so suppose that this is the equation, okay, we call the heat equation, okay, physically. You want to solve for u of xt, okay. To solve a general partial differential equation here, okay, we we might be able to find the way to reformulate the problem, okay, to be ordinary differential equation, so that we can use or apply the technique for ordinary differential equation to solve this partial differential equation. So that's the basic idea to tackle this type of problem. Okay, and one technique that has been very popular and also workable, okay, and said mathematically is we call the separable function technique. Okay, with to solve u of x, and this is a two domain, right, x and times. Okay, the separable function technique, okay, can help you to convert, okay, the problem here, okay, to the ODE, okay, ordinary differential equation, but as what we call the parametric. What we call parametric is that we're going to solve this ODE that rely on some parameter, okay, the new parameter will be added, and you will see that why they call this ODE become not only rely on the main domain x and t, they will have a new parameter we call small n, okay, that the discrete number of n equal to 1 2 3 4 5, okay, as an integer number is another addition, okay, to the resulting after to the result of the problem after you uh, convert the original equation to here to DOD. Okay, and then we can use the boundary condition and also the superposition. Okay, why superposition? Okay, when you having multiple input, okay, in the additive form, or also when you can separate the domain, okay, or the boundary condition into a union set. Let's just say that that you can decompose it. Okay, so therefore you can analyze for each decomposed element and use the result to combine it together. Okay, in the additive form. That's what we call the superposition technique. Okay, then you can find use this technique to find the general solution. Okay, one way of the separable function technique is that this is the key things that you might to remember. We're going to set up u of xt as the multiplication of two functions, and each function rely on each domain themselves. Like in this one, u of xt is equal to capital X rely on the small x domain times t that rely capital T that rely on the t domain. Okay, let's u of xt is a multiplication of two functions, while each function rely on each domain. Okay, and then you put u of xt here, okay, to the original partial differential equation that you are interested. In this case, we're gonna use the heat equation from physics course, okay, to solve it. But in general, okay, you can always apply this technique to this form, okay, of partial differential equation. Okay, so after this, you see that, okay, based on this, if you replace u by u of xt, and then you replace u of xt by these two separable function in the multiplicative form. Okay, it's obvious that you're gonna get this result. Okay, therefore curl u by curl t. Okay, certainly when you find the partial derivative of u with respect to t, so the function that rely on x become a constant because it's not the domain t that you are looking for the rate of change. Okay, so in this one, when you find the partial derivative, okay, x of x become, you know, become capital X as a function of the small x become constant, and so only derivative is here in the t term, okay, t domain. We represent here as a first order, okay, of t with respect to t. Okay, the same way we can analyze when you're using the second order here. Okay, when you want to find the second order of u with respect to x, okay, t, the capital T with respect to t is become a constant. Therefore, you find the second order of this function of x. This is a second function with a capital X with respect to a small x. Okay. Therefore, after you get this for this substitution, or after you set up u of xt as this separable function in multiplication form, you can put this result to the equation that you are interested. Okay, please really consider this, because this is the very quite unique technique that you can convert whatever partial differential equation, you can link them to what we call the ordinary differential equation, that you can use the technique that you studied previously to solve this problem. Okay, therefore, okay, when you using this replacing curl u by curl t and curl square u by curl x square, okay, with this formulation you get this result, because this is curl u by curl t is equal to alpha square, this is curl square u by curl x square. Okay, and then you move this term, okay, let's just say that if I'm using alpha, okay, divided by t sub t here, okay, over here, okay, because it's equal, you multiply both sides by alpha square and t, okay, this one divide by alpha square, okay, this alpha square, okay, cancel each other, and the division here on the left hand side become t pi t, okay, divided by alpha square tt. Okay, this function tt. Let's just say this. Okay, what we are doing is that we're gonna divide both sides by alpha square uxt. Okay, if you use alpha square times uxt here and use this replacement and divide it on both sides, this is the result that you're gonna get. You get t pi t. Okay, capital X by X is cancel each other, so the remaining part, okay, of the ratio is only t pi t divided by alpha square tt, because x is cancel each other. On the right hand side here, okay, alpha square cancel out and tt cancel out, so the remaining part is here, double pi x. Okay, we respond to small x, and with this equality sign of this side, okay, we're gonna assume that they're for some parameter we call alpha. Okay, alpha is not it can be any value. Okay, it's might be rely on both x and t. Okay, let's just say we're gonna assume that it's equal to, and we're gonna make the sign as plus alpha. Okay, we still don't know the sign of alpha, can be both positive or negative. We see the logic after this. Okay, so which means that these two is equal. We're gonna let them equal to some parameter we call alpha. That's why we call this a parametric ODE. Okay, if this is assumed to be equal to alpha, you end up, okay, having two type of differential equation. Okay, the first one here, okay, if you use this, the right hand side equal to alpha, you get this. Okay, therefore x double pi of small x minus alpha lambda time x is equal to 0, because you can see that these two is equal. Okay, if I multiply by x times x on both sides, okay, left hand side become second order of x, right hand side become alpha times lambda, sorry, I keep saying alpha, sorry, this is lambda x of x here. Okay, so you move that right hand side lambda times x of x to the left hand side. Okay, you get this equation the same way as you're doing here. This one is equal to lambda also, so you multiply, okay, this part, okay, on both sides. Okay, so the left hand side become t by t and the right hand side become this, and you move to the left hand side, you get another. So this one is that you the interesting part of this is that you now can, the original equation that you already have a two domain within and some partial differential equation term. Okay, you can convert them with this form of multiplicative of separable function here, okay, to a single domain, two independent single domain with a new parameter we call lambda. Okay, and also with the right hand side is equal to 0, to solve this function of x of x and t sub t, it's just solving all ordinary differential equation as a complementary solution that we studied in the first four clip, right? Because the right hand side have no additional function, therefore the only function of x of x and t of t is only complementary solution. There's no particular solution. Okay, so we're gonna try to look at each of these equation. Okay, the first one, okay, you get this equal to 0, and then you have boundary value problem. Okay, why do I get this x 0? Remember that the t we have a boundary condition of this. Okay, for any t, okay, you get u x of 0, okay, at t of t, and x of l t of t is equal to 0. Okay, so if you put this, okay, and replace it to here. Okay, so u0 t become x of 0 t of t equal to 0. Okay, since t of t can be non-negative, either negative or non-negative, or also can be zero also, but only condition that you can make sure that this at x is equal to zero, okay, u0t is always zero for all t, is you have to set up x of zero is equal to zero, right? That's the only way that this condition can hold. Okay, the same time as x is equal to L. Okay, when x is equal to L, you have x of L times t sub t is equal to 0. Okay, you cannot, unless t of t is equal to 0 for all t, which is meaningless. Okay, t of t need to have some non-zero function also. So only way you can make sure that u of L at for all t is equal to 0, you have to make sure that x of L is equal to 0. Okay, that's the result of this condition. Okay, so it become the boundary value problem, and you know that when you get this, okay, you get a characteristic equation, okay, for complementary solution, because second order term become s squared, first order term zero order term become 1. This is a zero order term, not first order term. So you have minus lambda equal to 0. Therefore s is equal plus or minus lambda. Okay, so suppose lambda is some specific value, and you know that for suppose lambda is greater than 0. Okay, if lambda is greater than 0, okay, this become 2 real root. Okay, and 1 is plus square root lambda without minus lambdas, and you all know that this is a general solution from the ODE procedure. Okay, you get a constant 1 e to the square root lambda of x plus c sub 2 e to the minus square root lambda of x. Okay, and when you put the condition here, x of 0, okay, x at x is equal to 0, the first this condition will be c sub 1 plus c sub 2 is equal to 0, because e to the 0 is always equal to 1. Okay, but when you place x is equal to L, you get this. This become coefficient, okay, to the square root of L, lambda times L, times c sub 1 plus e to the minus square root of lambda times L, okay, altogether times coefficient c sub 2 is equal to 0. So c sub 1 and c sub 2 here, okay, is the only way that this condition will be true is only that c sub 1 and c sub 2 is equal to 0. But if c sub 1 and c sub 2 is equal to 0, it's meaningless, because it means that x of x is equal to 0 for all x. So that become what we call a trivial solution. It's a solution that you don't need to find. Okay, it's obvious. For example, if you go back to the equation that if I set u is 0 function, okay, because now you have u is 0 function. Okay, why 0? Because you can see there is a multiplication. If x is 0 for all x, is why? Because look at this. Okay, for all x, if c1 is c2 is 0, x of x is 0, so you get no matter t as a function of t look like, u of x is 0 for all x of t. So when you put in this formula, 0 equal to 0, left hand side equal to right hand side, so it's meaningless. It's what we call the trivial solution, the solution that you can guess on first hand. So this example implies that lambda cannot be greater than 0. Okay, because if lambda is greater than 0, you get a trivial solution of u of x is equal to 0, which is, you don't need to, it's not the trivial. What we are looking for is that we want to find what we call the non-trivial solution. Non-trivial solution is mean that the solution that really have a unique identities, okay, and also uniqueness of the solution here. Therefore, with this illustration, we now can conclude that lambda cannot be greater than 0, or even lambda is 0 also themselves. Okay, if lambda is 0 themselves, is gonna take you can take a look at this both condition. It's not gonna help you also if both lambda is 0. Okay, so you're gonna end up having a trivial solution also. So this means that lambda need to be less than 0. Okay, but if lambda is less than 0, okay, this becomes the square root, the root of the characteristic or auxiliary equation become the complex number. So when lambda is 0 is less than 0, therefore your s function become plus or minus square root of 1, as I put this as j times square root of minus lambda, because you can see that both of these, if j is equal to square root of 1, square root of 1 times square root of minus lambda, it getting the result of square root lambda also. Okay, but we need to separate this, because since lambda is less than 0, if you put lambda less than 0 here, s become complex conjugate with the real part is 0. Okay, so but if you use minus lambda, it means that minus lambda is positive. If minus lambda is positive, so this one will become square root. It's not a complex number. Okay, it's a real number here. Square root minus lambda is a real, and times, okay, the complex here. So this one become complex conjugate with real part is 0 and imaginary part is square root of minus lambda when lambda is less than 0, which in general form is here. You can see that the exponent term is gone, okay, here. Why the exponent term is gone? Because the real part is 0. Okay, when real part is 0, okay, when exponential form is e to the 0 is always equal to 1. That's why the general form here, okay, for x function becomes c sub 1 times cos of the imaginary part minus lambda times x, okay, plus c sub 2 sine square root minus of lambda times x also. Okay, so we're going to use this with the boundary condition, okay, to track down the general form here. The same way that we did before. We have two conditions with x of 0 and x of L. You can see that when you put the domain x is equal to 0, you know that psi 0 is always 0. The second term is always 0. Only the first term here. When you know the first term here, when x is 0 is cos 0. Cos 0 always equal to 1. Therefore, the first one you get c sub 1 and x of 0 is 0, as I mentioned before. Therefore, you know that with this boundary condition here, x0 equal to 0, you get c sub 1 is equal to 0. So when c sub 1 is equal to 0, you know that with this general form, the first term is vanishing. Okay, only second term left. Okay, so the second term, what's happened with when you put x is equal to L? When x is equal to L here, okay, you get c sub 2 sine square root of minus lambda times L, okay, this one L, and you have to make this equal to 0, okay. One way, if you say that, okay, this implies also c sub 2 is equal to 0 also. If you use c sub 2 is 0, you end up going back to this form. It's a trivial solution. But there's some other way that we see non-zero c sub 2 is that if you put square root minus lambda here equal to n times pi divided by L. Look at this, okay? Because if square root lambda minus lambda is equal to n times pi divided by L, and you put it here, L cancel each other, you get sine of n times pi. With this, sine of n times pi is always equal to 0 when n is equal to 1, 2, 3 up to infinity. Okay, you can see that here, okay, is another we call the non-trivial solution. This is what we are looking for. If you get minus lambda is equal to n pi divided by L, no matter how C2 going to look like, it can be non-negative value c sub 2 here. This boundary condition holds. Okay, therefore, okay, in general form of x, x function as a domain x, okay, capital X, according to the domain x here, okay, is equal to c sub 2, okay, times sine n pi divided by L times x when n is equal to 1, 2, 3 to infinity. Therefore, n is another new parameter that adds to this function, because it depends on how you're going to put n here. N can be 1, 2, 3 up to infinity. Therefore, for each of this, okay, for each of this n, okay, C sub 2 can be different value. Okay, it doesn't have to be the same value because this one, the second term, is always whole for the boundary condition. Okay, so C sub 2 become function that rely on n, depend on how n going to be. And also x sub x here, okay, that the capital X function that used to rely on x also rely on the new parameter we call n here also, based on this non-trivial solution. Okay, so you can see that this is the resulting function of the x sub x that have some additional parameter we call small n is equal to a constant value times psi n pi divided by L times x. Okay, so this is the first part, okay, of to solve this results of this separable function technique. Okay, so the second part we consider the second equation here, this equation. Okay, when you consider this equation, okay, you can see that there's some linkage with this parameter of lambda here. Okay, now you can see that oh sorry, okay, here t by t plus lambda become lambda n. Okay, y plus lambda n here. Okay, you can might look here, you have square root minus lambda equal to n pi divided by L. Okay, n pi divided by L, but this one, okay, you want lambda, okay, time alpha square. Okay, lambda time alpha square. Okay, this one lambda is not square root of lambda. Okay, you can look at here that if you let's say that you use square root of minus lambda square become minus lambda. Okay, you get, because square root minus lambda, okay, you square them, you get minus lambda is equal to, you see that n pi divided by n square pi square divided by L square. Okay, and with the minus lambda here, okay, the original equation you have minus here. Okay, and lambda have the minus sign, right, because minus n pi square divided by L square, so minus times minus become plus. That's why this equation become plus sign. Okay, and the remaining term of lambda n will be here. Actually we start with minus lambda. Okay, that's why it's equal to minus. Okay, but you know that minus lambda from the original equation. Okay, minus lambda here. Okay, leading to the plus sign here, because this one you get when you get square here, okay, is equal to n square pi square divided by L square. Okay, and so the alpha square is the from the original equation, you can always have alpha square, and this one t by t equal to 0. Look at this lambda n here. Okay, that equal to n square pi square divided by L square. These are all positive, cannot be a negative value, right, because it's all square, right? When you know that this is all an alpha square have to be positive value, so you now know from the characteristic equation point of view, when you try to find the root of polynomial, in this case it's only one root because it's a first order problem. You can see that the first equation is a second order problem, the second problem is a first order problem. Okay, so this one become s because first order, plus this is a coefficient and multiply the zero order, you get lambda n divided alpha square, and lambda n is here. Okay, you might say that why minus psi is missing, because the original equation, okay, you have minus psi here. Once you put this, okay, minus lambda is equal to here. Okay, therefore lambda is equal to minus, so when you put lambda here, okay, minus times minus become plus. Okay, and and you change the remaining part, the alternate side of lambda become lambda sub n here, and you know that the root of polynomial here is s is equal to minus lambda n alpha square. Okay, we know that this have to be the real number. Okay, it have to, and also have to be a negative value, or not negative value, because you know that lambda is here is less than 0. Okay, okay, because lambda is 0, is less than 0, so this one become uh, you might say this one is less than 0, but this one become positive. Okay, this one become positive. Okay, because it is a sign changing based on the equation. So when you move here, you know that s have to be a negative value, the root of this characteristic equation, because lambda n here, okay, based on this positive alpha square positive, and you know that it's become a real number, negative real number. Therefore, t of t is, you know, the constant times e to the root st. S is here. You put lambda n as n square pi square divided by l square, and then you put alpha square here, all square, okay, times t, okay. And certainly now this one become t as a not only rely on function t, and also depend on what the n gonna look like, okay. Therefore, we are now ready to derive for the general function, because the u function, okay, also is this function times x as a function of domain x, and t is both capital X and t, okay, a function that rely on t, okay, domain t. So therefore, u of xt is these two functions multiply to each other. When they multiply to each other, the constant term can be rearranged to become the new term, like c sub 2n, okay, times c of n, no, c sub 2 rely on n times c times n, become a new constant, okay, rely on it. We call c star, okay, n, and this is e, this is from the t function, and this is from the x function, okay. When n is equal to 1, 2, 3, 4, 5 to infinity. Okay, this one is not only rely on x and t, we add a parameter we call n. Okay, but since this is there's another boundary value function that we haven't used yet. You remember that we have boundary value function here, boundary condition. Okay, here. Okay, we already used this too, but we haven't used this yet. Right, at t is equal to 0. Okay, u of x 0 equal to f of x. Okay, so this one is that we gonna use this boundary condition of u of x 0 equal to f of x when x is between 0 and l. Okay, by superposition principle. Okay, let's think about this. Okay, why? You can see that when t is equal to 0, let's look at u n x t when t is equal to 0. This exponent become the 1 because it's an exponent of 0, 0. Okay, so the only term remaining is this, the constant term times this sign term. Okay, but it's rely on n, and n can be 1, 2, 3, 4, 5, 6. If you want to combine all the effect for all n, okay, for all n, okay, therefore, okay, you know that when t is equal to 0, okay, this alphabet, when you to replace c is equal to 0, t is equal to, it becomes this coefficient here. We're going to call this c star n as b sub n. Okay, c star n at time 0, b sub n. Okay, times sine n pi x divided by l. Okay, but how many possible n? N can be 1, 2, 3, 4 up to infinity. This one we call the superposition. Superposition means is that, okay, you have f of x, okay, is equal to this for a specific n value, okay, and same f of x, okay, is for different n, okay. So you want to combine all the effect of this, okay, that can be represented as f of x, okay. So you use each of this effect of n in the additive form, okay. So you start from n is equal to 1 to infinity according to this. You have a constant value that you are looking for is b sub n, and as t is equal to 0, this sine n pi of x divided by l. Okay. So when you're using this boundary condition and superposition principle based on the additive, okay, why additive? Because n can be start from 1 to infinity. So you want to look at that for u of x 0, okay, for all n, okay, because when you, this one for u of xt for any specific n, but this one you say that this is u of x at time 0 for all n, okay, so you starting for each effect of n, okay, start and n is equal 1 2 3 4 5, okay, and you can see that for each n, okay, the domain t is separate, okay, so each function become almost independent for each n. So the resulting, okay, for u of x 0 for all n is in the superposition is in the additive function here. So this resulting of f of x, okay, is happen, okay, leading to this series here, okay. Okay, series means there is a summation from n is equal to 1 to infinity, okay, and therefore u of xt, okay, over here, okay, can be written here, okay, this is a f of x, and now you just add a term that you neglect when t is equal to 0 here, okay, you put this back, okay, why? Because now t is not equal to 0 anymore for all t. This one you know u of x 0, this one is u of x 0, but once you add t, the usual t term can be in this form, but as t is equal to 0, this term become 1. So you add this, and now you're ready to go, because now you have a very beautiful result of u of xt, which is the resulting of non-trivial solution for this one-dimensional heat equation. The reason we call one-dimensional, because you can say that we have two domains. Why you call one? Because the dimension of the object that you are interested in, you only consider the change according to one axis we call x, okay. You can easily extend when you try to move to the two dimension, therefore it becomes both x and y coordinate, and you can extend to three dimension with x and y and z, okay, which we will show you that is coming pretty soon, okay. So that's the result here in the, okay, but the key question of the solution in this in this form is that what is the b sub n, okay, and this is the new origin of the another question that asks that how b of n gonna look like, okay, and this is the resulting equation of this with this boundary condition leading to this f of x as a series, okay, summation of n is equal to 1 infinity, and you know that we all know that this series, okay, usually called Fourier series, okay. So who is Fourier? Fourier series is that actually Fourier is the last name of the French mathematician who derived a general solution for this heat equation. And this is the way that he come up with the resulting equation here, okay. And the remaining question is that what is the b sub n? How are we gonna find b sub n here? Okay, based on this equation, once you know the boundary, you know f of x here, okay, as a boundary value problem. If you know f of x, you can find how f of x gonna look like. You can find b sub n, okay, and to find b sub n here, okay, Joseph Fourier, okay, the guy who solved this question have derived it, okay, and the resulting is a beautiful result that you're going to see later. We call Fourier series, okay. So in the next step, okay, we're going to take a look at the different type of boundary value condition, okay. The boundary condition that we just gave you in this slide 43 here, okay, we normally call this based on the name of the people who started, okay, especially this boundary, okay. Certainly there are common boundary value, okay, sorry. This one is a common boundary value, but this one, okay, at the upper limit and lower limit of domain here, if you consider at the zero order condition, okay, like this is what we already solved it, okay, here, that we already get the result. We call this a Dirichlet boundary condition, okay. Certainly this is the last name of the guy who initiated this condition, okay. But there are some different type of boundary condition we call Newman boundary condition. If instead of using this u0t and u equal to lt is equal to 0, if we do just a first order condition here, you found the partial derivative of u with respect to t, the rate of change over time, okay, at domain at the lower limit domain, okay, x, and upper limit domain x, and both of these, if suppose this is equal to 0, if we use this condition, we call this the Newman boundary condition, okay. So what we are going to do next is that we're going to extend this, okay, and show you that, okay, we also can solve u of xt based on this condition, okay. Okay, we're going to go back to this resulting equation again, because this is x of x, okay, this is remember that, okay, from the previous analysis, okay. But we're not using this Dirichlet boundary condition. We're going to use Newman boundary condition. You can see here that, okay, when you need to find the derivative of x of x. You can't ignore the term because we don't use this condition anymore, so we're going to use the full term here. So this is the first derivative of capital X as a function of domain X, okay. This is c sub 1, and you find derivative of cos square root minus lambda times x, okay. So derivative of cos become minus sine, this is a minus, and then the constant square root minus lambda times x, okay, another derivative, and you derivative of cos, you get the sine, okay. On the latter term, okay, here you get derivative of sine, you get cos, okay. And certainly you need to have square root minus lambda times c sub 2, because you need to find derivative of what inside the sine function later, which is square root minus lambda of x. When you find derivative with corresponding to x, so it becomes square root minus lambda here, okay. So once you found this function, you use this Newman boundary condition. You get this, the first derivative function here is 0. So now the ball game changed, okay? Because when x now, the cos term becomes sine term, the sine term becomes cos term in the first derivative. So in this case, c sub 2 is 0. You remember that for this condition, c sub 1 is 0 because the cos term is here. But for the first order, the cos term become become here and times c sub 2, because therefore the sine term, when you put x is equal to 0, this sine term is always equal to 0. The remaining part is here, that if you want the first order term at times at the lower limit of domain x is 0, okay. So okay, no, yeah, when domain x is 0, okay, this cos 0 is equal to 1, so the only way is that c sub 2 have to be equal to 0. And then the same way, you put L here, when you replace x at L in the first order term, okay, you get the remaining term is here, is minus square root minus lambda times c sub 1 sine square root minus lambda L. This one you can find c sub 1. And the same way that we are doing with this condition here, you get square root minus lambda is equal to n pi divided by L, which c sub 1 can be non-zero. This only way that you get a non-trivial solution, right? Other way you have to make c sub 1 is equal to 0, that lead to a trivial solution. That doesn't that's not what we are looking for, okay. So once you get this, you can, with a similar analysis, you get this, okay. Therefore the remaining term is only cos function term, because now c sub 1 is non-zero, but c sub 2 is 0. So it's a reverse when you use Newman condition comparing to Dirichlet condition, because for Dirichlet condition, the sine term is the one that remains. But when you use the Newman condition that use the differential, the first order term instead of zero order term, when you apply the boundary condition for x at for the domain lower limit and upper limit of x, you get this x function that rely on n parameter of a domain x is equal to c sub 1 instead of c sub 2. This is cos n pi divided by L times x. And again, similar analysis, you will get this of t and t. Okay, that I already explained. There's nothing changed for tt. Okay, and therefore un of xt here become, instead of sine, become the cos term here. And with this boundary condition at t is equal to 0, okay, at t is equal to 0 for all domain x here, and with the superposition, therefore with this condition f of x have to be equal to here. What instead of you use b sub n, we call this a sub n here, because it's they not only they do not multiply with the sine function, become the cos function. So what I mean is that when you revert from using replace this condition with Newman condition, okay, everything go the same except the sine term become the cos term. Okay, so this is how the results come out. Okay. Oh no, sorry, here. Okay, the sine term become the cos term here. Okay, and therefore the general solution here is become like this. So very similar, and you need to identify different parameter. For the sine term we use b sub n, the cos term the constant parameter that multiply become a sub n, and it all leading to what we call the here. Okay, the series also, summation n is equal to c infinity. The second term is the same, so almost the same except the a sub n cos and b sub n sine. Okay, and the key question again here, okay, the same as we do when you use this condition. For Newman condition, how are we going to find a sub n? Okay, and a sub n is the coefficient of the series, and this series is normally called the Fourier series. Why? Because this is the way Fourier approach to solve the general form of solution for this physical problem, the heat equation problem in one dimension. Okay, so in the next step here, okay, we're gonna show you how you find b sub n and a sub n. Okay, you can see that b sub n and a sub n here all rely on the type of function of x here. Okay, function of x here. Okay, this is in general, to find a sub n, b sub n for all n, relies on the type of f of x. Okay, so before we're gonna show you how to use this, you might, first of all, you have to not confuse with the statement that I use here. I use here that suppose that we replace f of x by f of t, and this t is a different domain than t. Now t domain become the x domain, but t is not the same as when you're dealing with x and t simultaneously. You remember x is the dimension of the object that heat will flow, okay, and t is a time. But this one we consider, suppose that f of x is not the dimension of object anymore. We replace this as a domain t. So x and t is the same domain. But t here become the function according to time, okay? And it's the function that we call periodic function. What is the periodic function with period length of t? What is the nature of what we call the periodic function with period length of t? This is the definition of periodic function. If you can see that for all t, f of t is equal to f of the length of the period t plus t, which means that for any t between 0 to t, to capital T, okay, it will repeat themselves every t period, okay, whatever happened at t, okay, within 0 to t, okay, in the next period, okay, in the next period of t, okay, the same function will appear again and again and so on, okay. And we're going to write this, okay, f of t, okay, as a function here, as a constant function, a sub 0, plus summation n equal to 1 to infinity of a sub n cos omega n times t plus b sub n sine omega n times t, where omega n is 2 times pi times n divided by capital T. Okay, again, do not confuse with this t with this u of xt here. U of xt here is belong to that heat transfer problem, what we call the heat flow problem of one-dimensional heat equation. Okay, but t here is just try to make the characteristic of f of x here. Okay, which means that if f of x, okay, have a nature what we call the periodic function here. Okay, periodic function here. And if we consider f of t, okay, is in this form. Okay, is in this form. Just write f of t is in this form. You can see that it contains both cos and sine term. And we're gonna find the integral, okay, of f of t here, okay, over a period tau here, okay, tau here. So the length here start at t sub 0 is a constant t sub 0 to t sub 0 plus capital T, which means that for any period of time t sub 0, go to the next before the start the cycle of the next period t. Okay, we're gonna find the integral for all over here. Okay, so when you find the integral on these two sides, okay, you integrate, find the integral on this one become integral here, this one become integral cos and integral sine. Okay, this one we're gonna go back to definition of integral. Integral, if you want to find the area under the curve, it's obvious that if you have cos function or sine function, it's a sinusoidal function. You have both negative and like if you look at the sine function start from 0 going up and down for one period. Okay, the area is 0 because it's cancel each other. For the positive quadrant and negative quadrant, it's cancel each other. Therefore, the integral here, okay, for all period, okay, for you start any part of t sub 0, for the whole period, the sine have to be 0 for all n, and the cos have to be 0 for all n. Therefore, the integral within this summation is vanished if you try to integrate the whole period for any cos function or any sine function. Okay, if you can imagine the cos function, the sine function, doesn't matter what is the frequency look like. Okay, for the whole period, the area, okay, based on the sine of the amplitude of it, it's gonna cancel each other because it's the area up and area down. It's cancel to each other for the whole period. So it becomes 0 here. Okay, that's why we call it, since integral cos omega nt dt and integral sine omega t are the area under sinusoidal signal function, which always equal to 0 for all n. It doesn't matter how n gonna look like, or which is the frequency that you are interested here. Okay, so the remaining term is here, integral tau of f of t dt. I missed dt here. Okay, dt is equal to, okay, so in this one it's better. So the only term that left here. The nice thing about this, a sub 0 is a constant. So the resulting is that you, from the right hand side is a sub 0, you put it outside, and the integral dt from t sub 0 for t0 plus t, you get the upper limit minus lower limit. T sub 0 cancel each other, so you get t. So a0 times capital T is equal here. So you can find a sub 0 here. Okay. So this one is a sub 0 is equal to 1 over t integral t sub 0 plus capital T f of t dt. Okay. So with the knowing of f of t, you'll be able to find a sub 0. So you look back at the original problem. If you replace t by x, okay, you can find a sub 0, okay, is equal to 1 over t if your function of x is a periodic function. Okay, you'll be able to solve this in a general form when you knowing alphabet. Remember now you replace domain T, okay, as domain X, okay, and capital T is a cycle, but not according to time, according to the object that you are interested. Okay, so this is a general formula. You can find a constant effect, we call. It's a constant effect from any alphabet at the boundary condition here. Okay. Okay. Remember that we analyze as a small t, but when you bring it back to the general solution for partial differential equation, you have to replace t by x because the domain t is using another, it's a second domain in this problem. Okay, so this one is a sub 0. And now let's consider the other two terms here. Okay, how are we going to find a sub n, b sub n? You can see that a sub n, b sub n here. Okay, this is a key question we ask for. Given f of x, okay, given f of x here as a boundary condition, how do you find a sub n? And this is one is a Newman condition. For Dirichlet equation, how do you find b sub n? Okay, so we bring here, okay, all together here as a f of t here, okay, in this form. Okay, and we now know that, okay, if it's become the periodic function, okay, which mean that they have a repetitive form based on the period length or object length here. This is for every t length of object. Okay, in this case, when you apply back to the dimension of domain x, but this one we work on the domain t, you see. Okay, if we consider here, okay, if you want to find the cos term, okay, you multiply, okay, cos omega k times t. Okay, since this one, you summation n is equal to 1 to infinity, you multiply this by cos omega t, and then you find the integral on both sides again from over the period length t2 t by t. Okay, so when you get this, okay, and you know that you already know here integral cos here is equal to 0, right? No matter how a sub 0 is here, because when you find the area under the curve for any sinusoidal function, the area, okay, from the half width of a period will cancel out each other. Okay, so this one is 0. So you get here, you get cos and sin. Okay, because you add a more term of cos omega kt here. Okay, you have a sub n here, b sub n here. Okay, and then you find the integral on both sides, similar to what we are doing here. We find integral themselves because we know that when you integrate on both sides of this function themselves, the cos term and sin term will vanish. You can find a sub 0. Again, in this one, you multiply by cos for any omega k, and k can be any value from 1 to infinity. But we set up for specific k, not, but because n here you find all the summation additive effect for the right hand side. Okay, but this one time omega kt. So you have cos or sin. How you find integral of cos and sin? How do you change cos and sin or sin cos here? With one term is cos, you get cos. The other term you have sin, you get sin cos. Okay, we go back and trying to use this trigonometry property to change the product of cos and sin to the summation of cos. You know, this is a way back a high school trigonometry. Okay, cos a times cos b is equal to half of cos sum plus cos minus of ab. Okay, sin a cos b is equal to half of sine of sum minus sine of minus. Okay, you can easily find this in Google Wikipedia. Okay, how to prove this, but this is a benefit that therefore, okay, you're gonna look at this for each term of this integral. Okay, and then you can use this. Okay, cos become cos sum and cos minus. Okay, dt, and you can see that here. Okay, when n is not equal, when n is equal to k. Okay, when n is equal to k. Okay, let's just say when n is not equal to k. If n is not equal to k, it becomes the cos function. It becomes sinusoidal function of cos function, which you already know that when you find the integral of sinusoidal is equal to 0. Therefore, with this cos sum and cos minus, if n is not equal to k is become some specific some of the non-zero omega n and omega k. So therefore, when n is not equal to k, okay, when n is not equal to k, this term is always equal to 0. But when n is equal to k, this is what happened. Because when n is equal to k, let's look at here. This become cos of 0, right? Cos of 0. Because omega n is equal to omega k, this one become cos of 0. And you know that this become 1, okay? Cos here, okay? When n is equal 1 to infinity, okay? So this is 1, okay? This term, cos 1. And but this one is become cos 2 times of omega n or omega k, because omega n is equal to omega k, cos 2. And if you want to using another trigonometry principle, you can easily get that this is a cos 2 times of a plus 1. Cos 2 times of a plus 1 is equal to cos square of omega k of cos square of a. Okay, but when n is equal to k, this one because cos of 2 times of omega k, let's say cos 2 times omega k times t plus 1. So this is 2 times or cos twice of the angle is equal to cos square. Okay, cos square of this. Okay, that's another trigonometry that you can apply here. Okay, when cos of omega k and maybe the other way, the easiest way is that you when n is equal to k, you change this back to the original form, which means now you have cos when oh no oh yeah n a and b, yeah, when a and b is equal, okay, when a and b is equal, this one become cos square a, right? When a and b is equal, cos square a, when a and b is equal to each other, because a and b is equal. Okay, so this one, when n is equal to k, when you move back to the property, you get cos square. And when you look at the sign here, okay, the second term here, okay, the sine term, the sine cos term, the second term here. When you look at this second term here, okay, you get sine sum and sine minus. Okay, it doesn't matter when n is equal to k or not equal to k. This always 0. Okay, are you surprised? Not at all, because this is the integral of sine. Okay, okay. When both of these equal or not equal, okay, okay, you can always say that, okay, look at here, when this is equal or not equal, okay, because this term is always when n is equal to k, this one becomes 0. Okay, this one becomes 0. Okay, and this one is only you find the integral of sine here. When you find the integral of sine here, it's going to get you 0 also, because you know that integral of sinusoidal function. Okay, because you change from the product form to each cos and sine term, which you know that when you found integral is always 0. But just in only one case that happened is that when n is equal to k for this term, this one you need to find integral here of cos square here, and you can easily get here that integral t0 here, okay, cos square here, okay. And but you know that this one is a cos 2 times of angle A equal to 2 times cos square A minus 1. Therefore, cos square of A is equal to cos 2 times A plus 1 divided by 2. So you're using this to replace here. Okay. This one is at cos square. This is the angle A and omega k times t. You just put this substitution here. Okay. So this is the result here. Okay, and you know that the first term, when you have cos this one, the first integral is 0. So you have the only remaining term is the constant term here. But since they all divided by 2, dt start from t0 plus t0. So therefore you use upper limit minus lower limit, you get t value. Okay, but this division divided by 2. Okay, therefore, okay, we already show you that the only term left here is become t time divided by 2. Okay, and t divided by 2 here is, okay, multiplied by a sub n. Okay, no, a sub k, because it's happened when n is equal to k. Okay, so this one become a sub k. The second term is all 0. Okay, sine cos is 0. Okay, so that's why a sub k, okay, when you start k is equal to 1, is in this form. You can use the function of f of t times cos omega k times t integral here divided by 2 times t. So this one you can find the coefficient of a sub k. Okay, and in similar fashion for b sub k. Okay, for b sub k, instead of you use f of t times cos, you times sine. You get a sub 0 sine. This one is a we're gonna, when you use the sine here, you become cos sine and sine sine. Okay, now you're using a different type of trigonometry property here to use here. You get sine sine in the last term and cos sine here. Okay, and in a similar fashion you get b sub k in this form. Okay, very similar fashion that we are doing here. So this is how Fourier proved the general solution for heat equation here. Because in heat equation, doesn't matter when you're using Dirichlet condition or Newman condition, you end up having this formula, this general function here. But you have to find the coefficient of a sub n and b sub n. Okay, and a sub n of b sub n can be used by here. A sub 0 here, okay, you replace t by x. Okay, you find integral start x at t0 or to t0 plus t. Okay, f of x dx, and you have to make sure that your f of x is a periodic with a function, okay, that repeat themselves, okay, every t dimension, every dimension of x, the size of the dimension t, capital T here. Okay, you can find a0 here, and again a sub k here, you replace maybe a sub n here, you get here omega sub n and t replaced by x. Okay, f of x. Okay, this one you can find coefficient of a and b sub n here, just replace k by n and replace t by x. Okay, and make sure that you understand that the domain x are now running as a periodic. Okay, they have a periodic dimension, okay, for every t, capital T. Okay, so now you can show that this also the b sub k. Okay, so it's a little bit difficult. Okay, I'm sure that you have to repeat watching it several times. Okay, okay, first of all, I'm gonna conclude the key statement is that we want to solve the general solution here with this boundary condition. And there are two types of boundary condition. This one we call Dirichlet boundary condition and Newman boundary condition. For Dirichlet condition, this is in general form. But in this general form, you need to find the coefficient of b sub n. And coefficient of b sub n here rely on here. You can see that this condition, the boundary condition here. Okay, for given f of x, okay, f of x is equal to this one. And so b of n, okay, you need to solve based on f of x. Okay, you need, for given f of x, you need to find b sub n here based on this condition. Okay, and the same when you apply to the Newman boundary condition, you get this function. with this boundary value problem of f of x equal to this form. For a given f of x, you need to find a sub n. To be able to find a sub n and b sub n, okay, if you make sure that your f of x is a periodic function, okay, with the object length of t, okay, object length is mean that the object x, okay, instead of t we call period, okay, if they have some what we call the periodic function of f of x, okay, you can now, okay, based on this derivation, you can find the effect of in general form of a sub n and b sub n based on this formula, okay. All of them are going to have the constant effect of f of x themselves here, okay. Just remember that you replace domain t by domain x, okay, and a sub 0. And if you want to find a sub n, okay, just replace k to n here and replace t by x, okay. You're gonna get the way to find a of n, and this one for b sub n, okay, the same way, okay, for a given function f of x, okay. That's the, and make sure that f of x is a periodic function, okay. You might wonder and ask that if it's not periodic function, what's gonna happen? Yeah, you have to find this in the numerical way, right? Because you have f of x for all the domain of x, okay, equal to summation, it becomes an infinite equation. You can see that you have infinite unknown, a sub 1, a sub 2 to a sub infinity, and you have infinite function of x, okay, for all continuous of x. And how do you solve infinite system of equation? That's quite a difficult one, but you can approximate it by, cut down the term infinity to some finite term and solving as a linear equation system. Okay, so that will wraps up the first part of partial differential equation, okay, that we show you a complete derivation of the one-dimensional heat equation here, okay. Next time we're going to extend the way we analyze a problem in one dimension to a two-dimension problem. So next time we're going to move on to this slide of two-dimensional heat equation. Okay, so I'm going to stop now. Okay, we see you in the next clip.